welcome to all the audience. Very well, good noon. Today we start second lecture, third lecture, but second section of the talk. In the previous 2 days, we in fact developed the Riemann geometry very briefly. As I have said in the first lecture that Riemann geometry is the language to understand general theory of relativity. So, we shall start today general relativity. There are some video clips in this lecture, and in the beginning if you have any question from the last 2 lectures, please you can ask. So, we start the lecture. So, if there is no question, then this is the outline we have discussed in the first lecture. We have covered the first portion, Riemann geometry, in detail. Today we shall start general relativity. Obviously, this includes the special theory of relativity. But before that, I would briefly introduce how Einstein inspired to start or to develop the general special theory of relativity and then general theory of relativity. And at the end, I will discuss some interesting concepts, some interesting objects in this theory. Tomorrow is the last day. Tomorrow we shall discuss cosmology and exact solutions. Same books can be used to learn general relativity. This is one of the interesting things that all books start from the Riemann geometry, then give some brief introduction of special, and then general relativity and cosmology. So, you can consult any one of the books. So, let me start from the very beginning how special theory of relativity was developed and how Einstein inspired from the theory of electromagnetism. We all know these 4 laws of electromagnetic theory. First is the Gauss law for electric field, that is the divergence of E is equal to rho over epsilon naught. Here E is the electric field, rho is the charge density, and epsilon naught is the dielectric constant in vacuum. Second is the Gauss law for magnetic field, which is in fact the divergence of B is equal to 0. Here B is the magnetic field. Third is the Faraday's law, which is in fact curl of electric field is equal to minus partial B by partial T. And finally, the Ampere law, curl of B is equal to mu naught J. You can see here that epsilon naught and mu naught are particular constant. These are called dielectric and permittivity, magnetic permittivity in vacuum. Here rho is the charge density and J is the current density. You can see from the last equation, that is the Ampere law, that if we take the divergence of left hand side, this will be 0. However, the divergence of right hand side is not 0. This means this equation is not true in general unless we take a special case of steady state. So, left hand side of this equation cannot be equal to right hand side. This equation was improved by Maxwell, and by combining all these equations were called Maxwell equation. Before that, I would like to mention the values of these constants. Mu naught is equal to 1.26 into 10 raised power minus 6 Henry per meter, and epsilon naught is equal to 8.85 into 10 raised power minus 12 F over m. F stands for Faraday. As I have mentioned, the last equation, that is the Ampere law, does not hold in general. This is only for special case, that is a steady state. So, Maxwell in 1865 modified these equations. The only last equations, he in fact added this term. Now, if we take the divergence of this equation, both sides become 0. So, this equation holds in general. These set of equations are called Maxwell equations, and our theory of electromagnetism is based or revolve around these equations. Now, if we solve these equations, you can combine these equations to develop these two equations, and these are well known equations which correspond to the classical wave equation. Here you can see that v is the speed of the wave and f is an arbitrary function which depends upon x and t in one dimension. So, if we compare these two equations, we find that v is equal to c, that is the speed of light. So, Maxwell found that electromagnetic waves travel at a constant speed, that is the speed of light c. So, this is a very good result in the theory of electromagnetism, and this was called the greatest achievement in mathematical physics in the 19th century. This has satisfactorily explained a variety of phenomena like aberration, the propagation of light in moving bodies, phenomena observed in double stars, etc. This theory, the theory of electromagnetism, deeply impressed Einstein. So, he was convinced that a new transformation law had to be devised so that Maxwell's equation remain invariant in different frames. This was the main motivation of Einstein, that these equations must be coordinate invariant like tensors. But in this way, he has a main issue that the ether was the hurdle. So, because of the existence of ether, the law of propagation of electromagnetic wave cannot remain the same in two different frames. So, Einstein boldly rejected the idea of ether or the existence of ether in space. Now, as the law of propagation of electromagnetic wave would like alike in two different frames, but the question is with what speed? Einstein assumed, and for this assumption his companion criticized him, that the speed of electromagnetic waves should be the same in all frames, and this is the speed of light. So, Einstein adopted the following two postulates for the derivation of a new transformation. The first one is the principle of relativity. According to this principle, all laws of physics are same in any two coordinate systems in uniform relative motion. And second, the universal constancy of speed of light in vacuum. This principle says that the speed of light or the electromagnetic wave in vacuum remains the same in two different coordinate systems. Well, this was supported by experimental support for the non-existence of ether. Michelson-Morley experiment supported this concept. It is a well-known experiment in the 17th century. Huygens postulated the existence of an all-pervading medium called ether to develop the wave theory of light. But it has been discussed in the preceding slide how Einstein rejected the existence of this medium, that is the ether. However, the most famous test motivated to prove the existence of ether was conducted by Michelson and his student Morley in 1881. The outcome of this experiment disappointed them. So, we know that the earth is in motion through space. So, if there is a ether, the earth must have some velocity with respect to this ether. If this velocity can be measured, it would be a definite proof of the fact that the ether exists. Michelson designed an interferometer to measure this velocity, and this has been mentioned in his famous paper which is published in American Journal of Science in 1881. One can even see the details of this experiment on YouTube. The consequence or the result of this experiment is disappointing, as I have said. This is one of the famous null results in the history of experimental physics. But obviously, this was a crucial result because Einstein based his theory on this null result. Let me define some basic quantities. Frame of reference, it is more or less a fancy way of saying coordinate system. Inertial frame is a special frame in which the first law of Newton holds. An event is anything that can happen in space-time, for example, collision of two particles. So, we describe this event by 4 coordinates, that is the space-time coordinates t, x, y, z. Now, I come to the special theory of relativity, which was developed by Einstein in 1905. This theory says that an object moves with a uniform motion. In other words, we can discuss only things in flat space time. So, the formal basic postulates of this theory are: the first one, the principle of special relativity, that is, all inertial frames are physically equivalent. The second postulate is the principle of the constancy of the speed of light, that is, the speed of light in vacuum is constant for all inertial frames or for all inertial observers. Obviously, observer is sitting in the inertial frame. Next, we discuss some thing which is relevant to special relativity as well as general relativity, that is a 4-vector formalism. We all know about the position vector, which is valid in 3 dimension or 2 dimension. So, in 3 dimension, we just write down r is equal to x I plus y j plus z k, where I, j, k are unit vectors. But we always say it is a position vector, never say that this is a 3 vector. But in 4-dimensional space time, we have 4 dimensions t, x, y, z. So, we say it a 4 vector. Here you can see x0, x1, x2, x3, where x0 is time coordinate, but for the sake of dimensions of distance, we multiply it by c. So, this is ct. As you can see here, it gives the distance dimensions, while x1, x2, x3 are the coordinates x, y, z. Obviously, we can discuss its magnitude, like we have the magnitude of position vector is equal to x square plus y square plus z square square root. Similarly, we can have the magnitude of 4 vector. Here obviously, GAB is the Minkowski space time. This is given here, and we can write it in the form GAB. If we write in the matrix form 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1. So, obviously, I am taking the signatures plus, minus, minus, minus. In some books, people take these signs. I would use plus, minus, minus, minus. So, we can calculate obviously the 4 vector magnitude. This is given the Minkowski space in spherical polar coordinates. And similarly, if we have the position vector, then we can discuss the 4 velocity. Here is the 4 velocity. This dot represents derivative of 4 vector with respect to the proper time. Here c is the speed of light, v is the usual velocity in 3 dimensions, and gamma is the factor which is given in fact here like this, 1 minus v square over c square. We can calculate its magnitude. Let me mention how to calculate the magnitude of these quantities. This is the 4 vector momentum. 4 momentum is, as you know, momentum is just the product of mass with velocity. So here 4 momentum will be mass times 4 velocity, and I just explain how to calculate the 4 vector magnitude. This is the magnitude of 4 vector. Just write down like this: x square g00 plus x1 square g11 plus x2 square g22 plus x3 square g33. As you know, I have just mentioned that g00 is 1, g11, g22, g33, these are -1, rest are 0 because we have a diagonal matrix. So it means we have, this is 1, -1, -1, -1, and here x naught is ct. So here c square t square, this is 1, and here -1, here -1, this is x square, this is y square, z square. So finally we can write t square minus x square plus y square plus z square. So this is the magnitude of 4 vector. This is the way how to calculate the magnitude of 4 vector. Similarly, we can calculate the magnitude of 4 velocity. We have VA, VB, GAB, and we have defined VA as is equal to gamma CV. Here c is the speed of light and v is the velocity in 3 dimensions. Gamma is the factor I have already mentioned. So similarly, we can say v0 square g00, v0 v1 square g11, v2 square g22, v3 square g33. So v0, and this is obviously 1, and we can g11 is -1, -1, -1. So we can just write down v dot v. So it means I can write, and v0 I know that this is c, so I can just write v0 square minus v dot v square, here v0 square. So this means if I put the values of here, v0 is gamma c, so gamma square c square minus v square. So if we if I take gamma c square outside, then it is gamma square minus v square c square. Here it is it should it is gamma square, here it is common, here again gamma square is common, here it is 1. So this factor gamma square c square, and this is 1 over gamma square. So it means the magnitude of 4 velocity is t square. So we have shown that VA, VB, GAB is equal to t square. Now the question is, how can we find its magnitude 1? It is very simple. We can redefine, say, VA over C. So now we calculate the magnitude of VA, VB. This will be 1. Similarly, we can extend the idea of magnitude of 4 momentum, GAB, and you can see that P0 square minus P dot P. This is the magnitude of 4 momentum. In other words, we can also say that, okay. This is the magnitude of 4 momentum. And if we have 4 momentum or 4 velocity, we can discuss 4 magnitude, 4 force or 4 acceleration, because force is the basically mass times acceleration or time derivative of 4 momentum. So, this is the definition of 4 force, and we have just put the value of 4 momentum, and we can write in this way. Now, we come again, after defining 4 vector, we can write down the Maxwell's equations in terms of 4 vectors. So, these are the Maxwell's equations we have already discussed. Here is the 4 potential we can define. Here obviously, this is the 0 component and these are the special components. Here we have written down the value of A naught, which is phi over C. Here phi is the scalar field and A is the 3 vector potential. Okay. We know that Maxwell field tensor can be defined in terms of 4 potential as follows. As I have already mentioned in the first lecture, that this is the Maxwell tensor which is antisymmetric. So, if we swap the indices of this Maxwell field tensor, we have negative sign. So, using these things, I am not going into the details, but we can write down the Maxwell's equations which are 4 in 2. Here obviously, f a b comma b is the ordinary derivative is equal to mu naught j L A. This is the 4 current density, and this is a square bracket, which means this is antisymmetric. So, we can recover all the 4 equations from these 2 equations, which are available in the any book of special relativity. I am not going into the details of these equations. Okay, before starting the general theory of relativity, I would like to discuss a relativistic form of the energy momentum tensor for a fluid. In other words, I would like to discuss the perfect fluid energy momentum tensor. So, I would start from the classical hydrodynamics equations for the motion of a perfect fluid, which are given as follows. This is the well known conservation of mass. Here obviously, rho is the, it is because we are talking in perfect fluid, I mean fluid mechanics. So, this is the not the charge density, instead this is the density of the fluid. Rho u is the velocity of the fluid, and here f is the external force. So, the first equation is the conservation of mass, and second is the Newton's usual second law of motion, which is in fact we say that f equal to a. So, this is in fact f is equal to m a. Here this corresponds to the f, and this corresponds to the mass, and this is the acceleration. So, this is in fact f equal to m a. Okay, I would like to write to derive. First of all, I would write these equations in indices form. Then I would discuss how can we write these equations in a single form, and then we can discuss the perfect fluid energy momentum tensor. So, you can see from the first equation, this is rho is the scalar quantity. So, it remains the same, there is no index at all. However, we can write down this in the index form. Similarly, we can write down this in the index form, we can write this in the index form, we can write this in the index form. So, let me write down the first equation, partial rho partial t plus partial x I partial rho u I j is equal to 0. This is the first equation, you can say. I have written the first equation in this index form. Similarly, we can write the second equation, rho du I dt is equal to minus partial rho partial x I, this is the gradient of rho, plus f I. This is the second equation. So, now we know the well known formula of operators that d over dt is equal to partial by partial t plus u dot grade. This is the well known formula. I am just using this formula here, and if you say apply it on some velocity, that means you are applying like this, and then you can write partial ui partial t plus uj partial ui partial xi. Okay, now we use equations. This is number 3. So, we use now equations 2 and 3. What we are saying, that we put this value here in this. So, from 2 and 3 imply that rho partial ui partial t plus uj ui uxi plus partial rho partial xi is equal to fi. Say it number 4. So, we have just used equation number 3 in equation number 2. Now, if we multiply equation number 1 with ui, so we are just multiplying this equation with ui and add this equation to number 4. So, what will we get? Rho partial ui partial t plus uj partial ui partial xi, this is j, and then plus ui partial rho partial t plus ui partial by partial xj uij and plus partial p by partial xi is equal to fi. So, rearranging this equation, we can write partial x partial by partial t rho ui plus partial by partial x j rho ui uj plus partial p by partial xi is equal to fi. We have just rearranged that equation. Now, if we multiply and divide with c this equation, then we can write it, this will c will come inside because it is a constant, and when we multiply c with t, it will be partial by partial x naught. So, I can write it just partial by partial x naught and c rho ui plus partial by partial x j rho ui uj plus delta ij p is equal to fi. So, this is the equation here. Obviously, delta ij is the canonical delta, and this has the value 1 if I equal to j. This will be 0 if I cannot is not equal to j. From here, we can obviously write down the value of t mu nu. This is just a notation. It is rho square c rho c uj rho c ui rho ui uj plus delta ij. Now, this is all classical. We have just written down these things in terms of indices because we are going towards general relativity. Now, we assume a frame, a special frame in which particle frame is also moving with the particle. So, if one is sitting in the train and he doesn't look outside, it will look that he is at constant speed. So, we are in fact considering such a frame. This is called rest frame, in which the speed of the observer is constant. So, in this frame, obviously the components of velocity will be 0. So, we are considering rest frame. Rest frame means you are considering 4 velocity like this 0 c, this is a 0. Time component is the speed of light, while the rest of the components will be 0. That means this part which is u, this will be 0. So, if we take this assumption and apply on the expression T mu nu, this will change to some relativistic energy momentum tensor, and this will be like this rho c square 0 0 0 0 rho c 0 0 0 0 rho 0 0 0 rho. This will be obviously 4 by 4 matrix. And now we know that this expression can be written like this: T mu nu is equal to rho naught. Well, in the rest frame we can denote it by rho naught. So, this is rho naught plus P naught over C square u mu u nu g and minus g mu nu P naught. So, this expression is called the energy momentum tensor of perfect fluid. Here obviously P is the pressure, rho is the density, u is the 4 velocity, and g is the metric tensor. When there is no confusion, we can even omit rho 0 in the subscript, and we can just write down T 0 0 T say A B is equal to rho naught. Well, I just don't write. So, P over C square UA UB minus P GAB. This is the expression for the energy momentum tensor in perfect fluid. So, if we use this expression, we can write the relativistic generalization of the two equations in this form. So, obviously, this F A is the 4 vector force, and this is the energy momentum tensor for the perfect fluid. Here, comma means ordinary derivative, where I have written here. Well, in some cases, for example, in gravitational units, we take also T equal to 1. So, for this reason, here C is skipping. So, this is the energy momentum tensor for perfect fluid, and F A is the 4 vector. If in some case, in particular case, this 4 vector force vanishes, then we have the special expression, and this is the expression that, and this is well known expression of energy conservation. So, this is called conservation law obeyed by the fluid. Here TAB is conserved. Okay. Now we have a short video before starting the general relativity. This is about gravitation. So, please enjoy the video.
What is gravity? Two famous scientists did research on how gravity works. Newton was the foremost of them. What Newton is explaining about gravity is that all things in the universe have mass. There will always be an attraction between two objects, or every mass attracts every other mass. The gravitational force of an object also varies according to its mass. That is, an object with a greater mass pulls a lighter object to its side. The greater the distance between two masses, the less their gravitational force decreases. Force is inversely proportional to the distance to the power of 2. This means that if the distance increases by 2 times, the force will decrease by 4 times. If the distance increases by 3 times, the force decreases by 9 times. This is what Newton explained about gravity. Everything happens just as Newton said. The Earth orbits the Sun, the Moon orbits the Earth, and the universe itself works according to Newton's gravity. If the Sun's gravity is so strong, why didn't the Earth smash into it? Distance and angular momentum are relevant factors in this context. Well, everything's all right. This was accepted by everyone who was there then because it fits perfectly according to physics. But here comes the biggest confusion. The distance between the Sun and the Earth is about 150 million kilometers. Will there be a force for such a distance? For example, if I kick a ball, there is contact between me and the ball. So there is physical contact that makes the ball move. But what lies between the Sun and the Earth is the greatest distance. That being the case, scientists are gradually confused about what the kind of force that causes binding between such objects. And this is where Einstein joins. According to him, gravity is not a force, but it doesn't make sense. Why does it happen if there is no gravity? What's making it happen then? Which mysterious thing causes it? But his explanation for it, though not understood by anyone at the time, was understood a few years later. And it was that discovery that elevated him to an important scientist in the world. So, what was his discovery? Let's see how that works. Our universe looks like it is empty, but in reality it is not empty. Empty spaces are not really empty. The whole universe is like a fabric sheet. That sheet combined with fourth dimension time becomes spacetime. He says curvatures in spacetime are responsible for gravity. Let's take a fabric mat for example, and make a fat man sit in the middle of it, and make a skinny man sit on the edge of the mat. Now we will see that the mat bends inside where the fat man is, so the skinny man is automatically pulled towards the fat man. The fat man does not exert any force, and even if he doesn't touch him, the skinny man is drawn towards him. Similarly, gravity occurs for everything in the universe. As the sun bends space-time, the Earth is attracted towards it. It is not a force. As space bends, it has an impact on the objects on the curve. The mass tells space-time how to curve. Space-time tells the mass how to move. Now it's easy to explain how Einstein came to realize this. He found out the truth through thought experiments. Then the mathematical equations were also confirmed. He's sitting in his office one day when he sees a man cleaning the windows of a building close by. He starts to think about what would happen if that person fell down. While it may seem strange to us to hear this, Einstein describes it as the happiest thought in my life. Let's look at the things that crossed his mind. We will lock the man who was falling from the top of the building into an elevator. A man who is falling will not feel any force, since he is inside the elevator, and there is no reference point. He can't realize if he falls down or floats. The phenomenon of falling down as a free fall without any reference point is like floating in space. That is, according to physics, there is no difference between a person who falls from the top of a building and floats in space. Both of them wouldn't feel any gravitational force. So empty space weightlessness is equal to free fall on Earth. Let's move on to the next step. Now I'm floating in space inside the lift, and there's a ball also floating with me. A motor engine has been fit into the bottom of my lift, and I started that engine and accelerated the lift upwards at a speed of 9.8 per second square. 9.8 is 1g, the gravitational force for Earth. Now what happens when I accelerate at this speed is that the ball floating with me will fall down on the lift floor, and I will also be pushed towards the bottom of the lift. I feel the same amount of gravity on Earth as I feel inside the lift that is accelerating at a speed of 9.8 meters per second square in space. Whatever can be done with the help of gravity on Earth can also be done in this lift. I don't feel any difference, whether in space or on Earth. So free fall on Earth is equal to free movement in space. Gravity on Earth is equal to 9.8 meters per second square. Acceleration in space. That is, acceleration causes gravity. Now I'm in space inside a lift, and I turn off that engine, and the lift is made to float steadily in one place. What will happen if I throw the ball in straight? When I throw a ball, it goes in a straight line. What if I throw that ball at an accelerating lift? The ball will go down in a curved path and hit onto the floor. So far, everything is going well. Now I've switched from the ball to a light beam. How will it go if I torch the light in the accelerating lift? Light is known to always go in a straight line at constant velocity. If you throw a ball on the Earth, it will travel in a curved path and then fall to the ground. If the ball is thrown from an acceleration lift in space, it will also travel in a curved path. Does that mean light itself will be able to bend? Can light be bent even though it has no mass and always moves in a straight line? Einstein says it will bend. Yes, it is possible if there is something called space curvature, as he claims. How do we find it? The lift that is accelerating at just 9.8 meters per second square does not have enough opportunity to bend the light. So now, I changed the acceleration speed from 9.8 to 98. According to Einstein's prediction, the bend of light in acceleration at 98 meters per second square is very small. That is, it bends only the size of an electron. This means that if we increase gravity or acceleration, light can bend more and more. Well, how do we prove this? In those days, it was impossible to build an engine that had such acceleration and implement it. In fact, not even a rocket was invented at the time, but we have gravity. The sun was the strongest gravity when it comes to our nearby things. Its gravity is 28 times stronger than Earth's because its mass is 330,000 times bigger. If we calculate what will happen in that gravity, the gravity will bend the light to 1.75 arc seconds. An arc second is 360 degrees in a circle, and if you take 1 degree of it, it has 60 minutes within it, and 60 seconds per minute. Of these, 1.75 arc seconds is very small. In 1915, Einstein published his theory with equations. Everyone was confused when they saw this theory. What is this? What is he trying to say? No one understood it at the time. Then 4 years later, Arthur Eddington, the greatest astronomer at the time from England, set out with his team to experiment with this. At that time, they knew the exact location of some of the stars, and if Einstein's theory was correct, the star behind the sun should be visible somewhere else, because the light should bend and be visible to our eyes. They were waiting for a total solar eclipse because the sun's brightness makes it hard to see nearby stars. When the day of the solar eclipse came, Arthur Eddington's team started taking pictures. To their surprise, the star showed up in the photos in a place they hadn't expected. Gravity had bent light itself because space-time had been bent. For example, I go straight from one place to the North Pole. As far as I'm concerned, I'm going in a straight line, but to an outside observer, I appear to be taking a curved path. Similarly, light always travels straight, and because its path is curved, it also bends. So the shortest path of light can be a curved one. Now you may have a doubt. If the space at the bottom of a massed object only bends, does space bend at the top of that object? All the space-time curvatures we see in the video are shown in 2D visuals, so that we can easily understand them. Its 3D form is hard to understand, but that's exactly the case. It was only after this space-time curvature was demonstrated that Einstein was celebrated as the greatest scientist. This thought experiment is not a simple one. It is the greatest thought in human history. This simply explained not only gravity, but also showed the world how the entire universe works. This is called the general theory of relativity. That's what space-time curvature is. But how did this time come in it? How does space-time explain time dilation? The special relativity theory provides an explanation, and we'll see it in detail in the next video.
Okay, let's start again. Now we start the general theory of relativity, and as you know, special theory of relativity is the special because special in the sense it holds only for uniform motion. This was developed in 1905, but Einstein spent almost 10 years to generalize this theory, and this is true for arbitrary motion. Again, he based on the following two postulates. The first one is the principle of equivalence, that is, the gravitational and inertial forces acting on a body are equivalent and are indistinguishable from each other. Say we have gravitational force and inertial force, and we can have the gravitational and inertial mass. The second postulate is about the general covariance. The laws of physics are covariant, or they remain invariant under coordinate transformation, just like we have the tensor quantity. So, on the basis of these two postulates, well, this postulate says that if we have a force like this in one coordinate system, this will also be true in some other coordinate system, for example, in spherical polar coordinates. Or if we generalize it to 4 dimensions, then this force in Cartesian coordinates, it is true in any other general coordinate system. After giving these postulates, Einstein developed his famous field equations, that is called Einstein field equation. Let me mention here, Einstein didn't derive these equations, but he considered some steps to formulate these equations. These are given in very few books. Usually Einstein field equations given in the books is through variation principle. So, I would mention these 4 steps. Firstly, he in fact used the 2 postulates to formulate these equations. Firstly, according to the principle of covariance, the field equations must be in the form of tensor, as general covariance principle says that the quantity remains same in different frames. So, this corresponds to the tensor quantity. So, the field equations which will be formulated must be in tensor nature. Secondly, we know that there is a well known Poisson law of gravitation in classical mechanics. So, it means this is mathematically given in the form. Here psi is in fact the scalar potential, g is the gravitational constant, rho is the density, mass density, 4 pi is usual constant. So, it means the new equations developed must reduce in this form. So, in fact, we shall make the correspondence of the new equation with this equation. Now, how can we make correspondence? We know that in the general theory of relativity, metric tensor is the basic ingredient. This have 10 metric component functions that correspond to a single scalar function psi of Newton theory. So, it means new law must not contain higher derivatives of the metric tensor than the second, because we have the Poisson equation in the second order. Now, we know that the metric tensor contains second order only in Ricci tensor. So, the Ricci tensor indeed does not contain higher derivatives of GAB than the second. So, this is the appropriate to consider the Ricci tensor. So, the left hand side of the resulting equations must be in RAB. And the third place, we consider the right hand side. We have seen in Poisson equation the right hand side is 4 pi g rho. So, 4 pi g is constant and rho is the physical quantity. So, it must relate in the new formulation to the energy momentum tensor for a fluid. So, according to special theory of relativity, the conservation law in flat space time is given as follows. We have just seen in previous slides. So, now we know that in geodesic coordinates, the first derivative of the metric tensor is 0. So, this means the Christoffel symbol in the geodesic coordinates is 0. So, if we use these coordinate system, then we can write the conservation equation in the following form. Here obviously semicolon means covariant derivative. So, it means this equation is also true in geodesic coordinates. So, if some equation is true in locally in geodesic coordinates, we can extend this idea to any coordinate system, as the tensor equation is valid for any coordinate system. So, we can say that this equation 3 is true for a curved space time. Finally, the last step in the formulation of these equation is that RAB Ricci tensor must have the expression such that its covariant derivative is 0. And we know that this is equal to this is in fact the Einstein tensor. So, if we combine the 4 steps, this led to the Einstein to write down his famous field equations as follows. These are the famous Einstein field equations. Here obviously we can say that kappa is the gravitational constant, kappa is the coupling constant, which couples in fact the geometric and matter part, as the left hand side of these equations is the geometric part, right hand side is the physical part or matter part. As I have said that this is the Einstein tensor, which is equal to this. So, now we can see from the field equations, these are the 10 coupled highly nonlinear second order PDEs for 10 functions of 4 variables. You can see RAB, which is a Ricci tensor, it indicates the second order. GAB contains the 4 vector, it means it is a partial differential equation. Now, GAB is multiplying with R Ricci scalar, and Ricci scalar also contains derivative. So, it creates the non-linearity in the field equations. And as we know that metric components have 10 independent components. So, it means we have 10 functions of GAB, that is 10 unknown. So, this is a complicated system. Due to the nature of the Einstein field equation, Einstein predicted at that time that it will be impossible to find for anybody the solution of these equations. However, this was a surprise for Einstein when Schwarzschild found a very well known solution within 2 months after these equations. After Schwarzschild, there are many solutions, lot of solutions in fact have been found. Some of these solutions are very interesting, physical, but others provide only the mathematical nature. Many different techniques have been used to find these solutions. Then these solutions are classified according to a Lie algebra structure generated by the space-time. As I have discussed Lie algebra structure yesterday, that how to generate the generators, and then how can we check whether this algebra is closed or not. So, they have these solutions can be classified accordingly, and many classifications are given in the exact solutions book, as I have mentioned the list. Then Einstein believed that this universe is static. Before applying to the cosmology, this was the belief of Einstein, that this universe is static. So, in fact, he reformulated the field equations by introducing a term, this term. So, this is the cosmological constant, well known cosmological constant, but later on Hubble proved that the universe was expanding. This is not a static universe, but it is expanding. So, Einstein accepted his idea and threw out the cosmological constant from his equation by saying that it was his biggest mistake of his life. However, recent observations indicate that some type of vacuum energy is at work in the universe. So, the role of this cosmological constant is very significant in the cosmology. Now, I just give some glimpses how to find or develop Einstein field equation through variational principle. In this procedure, we use the action and its variation. So, the action will generally consist of a matter part and a part for gravity denoted by Sg. Apart from the action, for other fields that are present like electromagnetic field and many others. We start with this action, which is the matter part and gravitational part. The matter action involves the metric tensor as follows. Here we have written down the action for the matter part. Let the action be varied due to a variation in the metric tensor, say delta GAB. Now, the total action must be invariant. So, it means delta S should be 0. So, now we need to solve this system, but I am not going to give the details or solution here. I just write down the equations. So, the action for gravity independently proposed by Einstein and Hilbert. For this reason, this is called Einstein-Hilbert action, very well known. So, here gamma obviously a constant that will be involved in the coupling of gravity to matter. So, solving this variation principle equation, we can have the Einstein field equations, which we have already written. So, after these equations, I would just discuss two applications of these equations. First, the Newtonian limit of the field equation. I mean, when we apply the Newtonian limit on the field equation, they reduce to Poisson equation. Similarly, when we apply some limits on the geodesic equation, they reduce to equation of motion in classical mechanics. As a principle stated by Einstein for the development of quantum theory, special and general theories of relativity is the correspondence principle. This principle says that every theory must reduce to Newtonian theory in some appropriate limits. So, it is the requirement in the appropriate classical limit the theory should reduce to Newtonian physics. The reason for this requirement is that in the usual region, Newtonian physics provides a very good description of nature. So, we say that Newtonian physics is not a wrong theory, but we generalize the other theories, and that must reduce to this theory in some particular limits. There could be infinitely many theories to be stated in principle. For them to be acceptable as descriptions of nature, they must be consistent with the Newtonian description in the usual region. For example, if we say quantum theory, the classical limit is that the Planck constant must go to 0. For special theory, if we say C tends to infinity, it reduces to Newtonian theory. Similarly, for general relativity, C tends to infinity or ui is equal to x dot I are negligible, and a space approximate to Minkowski space time. So, first we reduce it to special, then special to Newtonian theory. Further, assume that the first derivative of the metric coefficients are small, so that their squares can be neglected, and that the geometry is not time varying, that is, they are static space time. So, to check the validity of the Einstein field equations, we need to verify that they reduce to the corresponding equations for the Newtonian gravitational potential, and the geodesic equations reduce to the equations of motion in a gravitational field. So, we now return to the relativistic treatment of gravity. First of all, we shall consider the geodesic equations. We know these equations, that x double dot A plus Christoffel symbol into x dot P into x dot C is equal to 0. We have discussed these equations yesterday, and today we shall, because obviously this is the consequences of gravity. So, how will we shall see here how these reduces to these equations reduce to the classical equations using the weak field approximation. So, as we have seen in the last slides, that these are the limitations when we reduce the field equations to the classical mechanics. So, we shall use these equations to write down the geodesic equation in the form. So, here we have taken gamma symbol 0 0 instead of AB. The reason is xi dot is 0. So, we have taken only the non-zero values. Okay. So, as we have seen in the last slide that this x dot 0 is 1. So, we have reduced this equation to in this form. Okay, now your definition of the Christoffel symbol gave us this value. So, inserting this value in equation number 5, we have the following equation, which is number 6. Now, from 6 we can write down, we know that G00 is equal to 1 plus 2 psi over c square in the classical limits. Here psi is the potential, c is the speed of light. Obviously, when c tends to infinity, this reduces to 1. So, using this result G00 in the previous equation, here inserting this value of G00 here, we obtain this equation. This is the well known equation of motion in classical mechanics. Obviously, this is due to gravitating object according to the Newtonian theory. So, at a large distance from the object, psi scalar field goes to 0, so that G00 goes to 1, as I have discussed earlier. Next is the Poisson equation from Einstein law. As we have seen that we have in fact formulated Einstein field equations by using or with the correspondence of Poisson equation. Here we are going back. We are considering Einstein field equations, or you can say Einstein law of gravitation, and we reduce it to Poisson equation. So, we consider a very weak gravitational field and static distribution of matter such that the pressure is negligible as compared to energy density. So, in this case, the non-zero components of the energy momentum tensor are the following: T00 is equal to rho c square, while the rest of the components will be 0. Okay, let me give some details. We know that R A B minus half R G A B, these are the field equations, and we can write down the trace of these equations if we multiply these equations by G A B. R G A B G A B is equal to kappa T A B G A B. Obviously, this is in fact the Ricci tensor, Ricci scalar, sorry, and this is you can say number 4, as we are dealing with in space time. So, that means we have left here R kappa T. So, this means minus R is equal to kappa T. Inserting this value here. So, R A B plus 1 by 2 kappa T G A B is equal to kappa T A B. So, this means I can write down R A B is equal to, kappa is the common factor, T A B minus half T G A B. So, in other words, we can say that the Einstein field equations can be written in this form. Now, obviously, from here we can write down R00 is equal to kappa T00 minus half G00 T. We have found already that this is rho c square. This is also rho c square because rest we have only T00 component is non-zero, as we have seen here. So, trace will be just rho c square. So, in inserting these values in this equation, here we can have the following form of R00. Now, through the well-known formula of the Ricci tensor, we can also write the value of Ricci tensor here. So, if we compare these two values of the Ricci tensor found through the Einstein field equation and the usual formula, we can have the equation like this, and this is the well-known equation of Poisson equation if we choose kappa is equal to 8 pi g T4. So, in fact, we have considered the Einstein field equations, we applied the limitations, and then we arrived at the Poisson law of gravitation, and we have also found the value of coupling constant. So, next we come to the solutions of the Einstein field equations, and the first well-known solution is the Schwarzschild solution that was found in the same year when Einstein developed his field equations. We all know that the Einstein field equations are a set of 10 partial differential equations for 10 functions of 4 independent variables. I have already explained this thing. They are second order and highly nonlinear. The nonlinearity is in both first and second derivative and cannot be assigned any degree as the derivatives are multiplied by the inverse metric tensor. We have already seen in the Einstein field equations. So, the problem of solving the field equations is obviously too complicated to resolve in any degree of generality. So, instead of attempting a general solution, some physical relevant matter tensor is chosen and assumptions are made about the space-time symmetries of the solution. So, in this way, the number of independent variable and the number of functions to be determined is effectively reduced. A further reduction is achieved by appropriate choice of coordinates. For example, we can choose spherical system, cylindrical system, axial system, and any other, so that we can reduce the complications. In choosing all these assumptions, the problem is still complicated. So, here we start off with the simplest case, that is the vacuum case. Here in vacuum case, we have the trace of the energy momentum tensor 0, and we obtain the maximum symmetry. We know that in 4 dimensions, maximum symmetry is achieved with 10 Killing vectors, and that is the Minkowski space-time. In Minkowski space-time, we have 10 Killing vectors. So, on account of physical relevance, we will be here interested in solving the vacuum field equations with spherical symmetry. So, the target is to solve the spherical symmetry with vacuum space-time. There are non-vacuum solutions as well having spherical symmetry with 7, 6, 4 and 3 Killing vectors. Even though we are taking vacuum case, that does not mean that there is no matter anywhere. We only assume that there is none in the region under consideration at particular place. Similarly, there are no stresses or energy in that region. Since there will be gravitational effects, it should be borne in mind that gravity will not be regarded as providing any energy. As such, the energy of test particles will not generally be conserved. So, we start by considering a point gravity source of mass m in its own rest frame that is situated at the origin. This implies that the solution is spherically symmetric, and excluding the origin, there is a vacuum. Mathematically, we can write the most general spherically symmetric metric as follows. Here you can see nu, lambda, r are general coordinates, general functions which depend on time and space coordinates. Here obviously r, theta, phi are the spherical polar coordinates. Now, for the point mass, the gravitational field cannot vary with time. This means we need to consider these arbitrary functions as time independent. So, the metric reduces to this form. Now, there are two possibilities as regards R. It can either be constant or it has varying function. In the first case, when we consider is constant, this becomes unrealistic. So, because it is because we are considering the gravitational mass. So, we are not considering this case, the first case. So, we are taking now the second case. In the second case, we need to redefine the radial coordinate to be r instead of small r. So, the metric becomes in the following form. Here, this is the final metric we are considering. Here, nu and lambda are unknown, which we are going to find through vacuum field equations. In fact, when we consider the vacuum field equations, we say that r a b minus half r g a b is equal to kappa T a b. That means this is equal to 0. So, as we have seen from the trace of the equation, this leads to R A B is equal to 0. So, it means in vacuum case, the Einstein field equations mean R A B is equal to 0. So, we are just need to find the components of the Ricci tensor. So, R00 component is here, R11 component is here, and you can see from these components, when we add these two components, we are left with only this term. And these two equations imply that nu is equal to minus lambda. So, in fact, we have two non-zero constants, non-zero functions, but here from these two equations, we are reduced to only one. Now, using this output in the R22 component, here is the R22 component, and when we integrate this, we find e raised to power minus lambda is equal to e raised to power nu, and this is equal to 1 plus alpha over r. Here obviously alpha is an arbitrary constant or integration constant. Due to spherical symmetry, we can always have like this R33 is equal to R22 sine square theta. So, we do not need to consider or calculate this thing. So, we have therefore a complete solution of the Einstein vacuum field equation with spherical symmetry in this form. This is called the Schwarzschild solution. The constant alpha can be found through the condition on the boundary, and this is given by alpha equal to minus 2 g m over c square. Obviously, this here g is the gravitational constant and m is the mass, gravitating mass. So, this is the complete solution of the Schwarzschild solution, which is the complete solution of vacuum Einstein field equation. Next is the Reissner-Armstrong solution. This is in fact the X-charged version of the Schwarzschild solution. Reissner and Armstrong together found a solution. I am not going into the details of this solution. We just writing down the solution and describing these. So, the metric is given here. Here obviously, we are considering the coupled Einstein-Maxwell field equations to write down the solution, and the solution is given here. This is the Rn solution. Here obviously, this is the extra term which is coming due to the charge. So, here q is the charge, rest if you make the q equal to 0, this reduces to Schwarzschild solution. The next some complicated solution is curve and charge curve matrix. Here you can see this solution was found initially in 1967, and this is also a solution of the Einstein vacuum field equation, but here we have a rotation. It was originally obtained using spinors and requiring that the solution be a rational function. So, again we are going to just write down the solution and describe its nature. This is curve metric, not the Rn matrix. So, this is the curve metric given here. Here obviously the terms using are rho and delta. So, obviously here the new parameter is A, which is the important parameter, because this is the rotation parameter, and you can see it is complicated in the sense that we have off diagonal element. So, if rotation parameter is 0, we reduce it to some other matrix. So, this metric represents a point mass with intrinsic angular momentum m a. Due to the spin of the gravitational source, inertial frames are dragged along with the rotation. The Kerr metric is the solution of the vacuum equation. Kerr also found a similar solution of the Einstein-Maxwell equations corresponding to a spinning or spinning charged, you can say to a corresponding to a spinning charge mass. This is the generalization of the Rn metric. This solution was also obtained by a neat trick of complexification by Newman. So, for this reason, this solution is called charge curve or the Kerr-Newman metric. It is written like this. As we can see, this here is the additional charge term, and now we consider the special cases. Kerr-Newman metric reduces to Resident-Armstrong metric when we take the rotation parameter 0. This metric reduces to the Kerr metric when we take q is 0. Further, we can see that Rn metric reduces to Schwarzschild metric when q is 0. And finally, Kerr metric reduces to Schwarzschild metric when the rotation parameter is 0. Next, we discuss the linearized gravity. We all know that the GR is nonlinear, and obviously nonlinearity gives some motivations, but we can have some more insights by considering its linear form. Since the field in GR is the metric tensor, its appearance in the metric equations nonlinearly gives rise to the nonlinearity of general relativity. We cannot change the way the metric tensor enters into the curvature, but we can write the curved spacetime metric as the flat or Minkowski spacetime metric tensor. So, we define the metric tensor. This is the general metric tensor. So, when we define the linearized gravity, that means we are splitting it into the Minkowski spacetime plus some function which is a very small function, and its higher powers can be neglected. Let us define the inverse metric as follows. I am not giving the details how it can be written, but we can always calculate this thing. So, this is the inverse. Here this function can be calculated, and when we insert this function into this, then we have the inverse of the metric tensor. So, we can always calculate this. This is the inverse of that. I am going a bit details how to calculate this linearized Christoffel symbol. This is very simple. We know the definition of Christoffel symbol ABC is equal to half GAD BDC plus TDB minus BCD. This is the usual definition of the Christoffel symbol. So, we use here GAB is equal to eta AB plus HAB, and its inverse GAB equal to eta AB minus HAB, as I have just defined here. So I'm using this definition. So inserting these values here, we can write ABC is equal to 1 by 2 eta AB minus HAB, and then BD means eta BD plus HBD comma C, then plus eta CD plus HCD comma B minus eta BC minus plus HBC comma D. Now you can see, because this is the Minkowski space-time, its derivative will be 0. So in all cases this becomes 0. So in fact we are using this symbol because this is approximation 1 by 2. Now you can see from here we are left inside HBD comma C plus HCD comma B minus HBC comma D. Okay, this is okay up to here. 1 by 2 eta AB HBD comma C HCD comma B HBC comma D. However, when we multiply this term with these terms, it becomes the square power of H. As we know that H is a small quantity, so its higher powers can be neglected. So finally we can see that this is the linearized form of the Christoffel symbol. Now using this Christoffel symbol, we can write down the value of Ricci tensor. So this is the form of the Ricci tensor when we linearize it. Obviously, when we linearize these things, we can write down the linearized form of the Einstein field equations, and here are the Einstein field equations in the linearized form. Here box means 4-dimensional operator, and phi EB is the some scalar linearized tensor, and TIB is the Ewell energy momentum tensor. Obviously, when we have the vacuum case, phi AB satisfies the wave equation. Here you can enjoy the video, small video. Before starting the applications of GR, this is a very small video clip, almost 3 minutes. Okay.
Black holes are among the most fascinating objects in our universe, and also the most mysterious. A black hole is a region in space where the force of gravity is so strong, not even light, the fastest known entity in our universe, can escape. The boundary of a black hole is called the event horizon, a point of no return beyond which we truly cannot see. When something crosses the event horizon, it collapses into the black hole's singularity, an infinitely small, infinitely dense point where space, time, and the laws of physics no longer apply. Scientists have theorized several different types of black holes, with stellar and supermassive black holes being the most common. Stellar black holes form when massive stars die and collapse. They're roughly 10 to 20 times the mass of our sun and scattered throughout the universe. There could be millions of these stellar black holes in the Milky Way alone. Supermassive black holes are giants by comparison, measuring millions, even billions of times more massive than our sun. Scientists can only guess how they form, but we do know they exist at the center of just about every large galaxy, including our own. Sagittarius A The supermassive black hole at the center of the Milky Way has a mass of roughly 4 million suns and has a diameter about the distance between the Earth and our Sun. Because black holes are invisible, the only way for scientists to detect and study them is to observe their effect on nearby matter. This includes accretion disks, a disk of particles that form when gases and dust fall toward a black hole, and quasars, jets of particles that blast out of supermassive black holes. Black holes remained largely unknown until the 20th century. In 1916, using Einstein's general theory of relativity, a German physicist named Karl Schwarzschild calculated that any mass could become a black hole if it were compressed tightly enough. But it wasn't until 1971 when theory became reality. Astronomers studying the constellation Cygnus discovered the first black hole. An untold number of black holes are scattered throughout the universe, constantly warping space and time, altering entire galaxies, and endlessly inspiring both scientists and our collective imagination.
With black hole, an important and interesting concept in general theory of relativity. Let me first define what is black hole. This is a region of space-time where gravity is so strong that nothing, not even light, can escape from its pull. It is formed when a messy object collapses under its own gravity, compressing its mass into an infinitely dense point, which is known as singularity. And this is surrounded by an invisible boundary called the event horizon. A rotating black hole is surrounded by the ergosphere, a region in which the black hole drags space itself. Now, let us discuss the types of black holes. Schwarzschild black holes, which we have discussed, Schwarzschild solution. In fact, this describes the Schwarzschild black hole. They don't have rotation and even don't have charge. Next is the RN or Risner-Armstrong black holes. They don't rotate, but they have charge. Next is the Kerr black holes. They have rotation, but they don't have charge. And the most general Kerr-Newman black holes, they have rotation as well as charge. So these are the four well-known black holes. There are many others, but I'm just discussing the initial one or the basic one. Now, this is a general concept that there are only 3 parameters are required to describe a black hole structure, as we have seen. Number 1, mass; number 2, charge; number 3, rotation. For this reason, there is a well-known theorem about black holes, that no-hair theorem. This means 3 parameters completely describe the structure of a black hole. Next interesting concept is gravitational stars. That means grava means gravitational, stars VA means vacuum, and stars star. So gravitational vacuum star. This is an object with a core of exotic matter. They are surrounded by a shell of ordinary matter. It appears when a collapsing star performs a phase transition. Exotic matter is created before the event horizon is formed. So such an object will be as compact as a black hole. Now, let's make a comparison between black hole and grava star. Externally, a grava star appears similar to a black hole. There doesn't seem any difference. However, black holes and grava stars can be detected by observing X-rays emitted by falling matter. So it is also similar. Current accepted black hole models have a very large entropy, while grava stars, on the other hand, have a quite low entropy. So this is a difference. Then black holes have event horizon as well as singularity, while grava stars have no event horizon and no singularity. This is a big difference. Grava stars consist of a compact object with an interior D-star coordinate condensate matched to the shell of shell of finite thickness, which is further matched to an exterior Schwarzschild vacuum solution. Thick shell replaces both the dister and the Schwarzschild horizons. Therefore, the gravastar model has no singularity at the origin and no event horizon, as its rigid surface is located at a radius slightly greater than the Schwarzschild radius. The first model, or the pioneer model of gravastar, was proposed by Mazur and Mottola with 5 layers. Number 1, an interior dister vacuum. Number 2, an infinitely thin shell. Number 3, a finite thin layer. Number 4, another infinitely thin shell, and finally the exterior Schwarzschild vacuum. However, this was revised by Visser and Wilshire, and they adopted a simple model with only 3 layers. Number 1, an interior dister vacuum. Number 2, one infinitely thin shell, and finally the exterior Schwarzschild vacuum. And nowadays these 3 layers are used to discuss gravastar. Here is a video clip, very brief video clip. Now finally we discuss wormholes. This is also an interesting object. This is a solution of the field equations which acts as a shortcut associating distant regions of the space-time through a handle or tunnel. There are 2 types of wormholes. Number 1, inter-universe wormholes, connecting distant regions of the different universe. And intra-universe wormholes, they connect distant regions of the same universe. Now we can discuss non-traversable wormholes, a wormhole that doesn't allow the two-way motion of an observer across distant regions of the universe. This is called non-traversable wormhole. While Well, the first non-traversable wormhole solution was suggested by Einstein and Rosen in 1935. For this reason, it is called Einstein-Rosen bridge. Then is the traversable wormholes, a wormhole which allows the observer to move freely in both directions from one region of the universe to the other. This is known as traversable wormhole. And finally, this video will provide the details about the wormholes, both traversable as well as non-traversable wormhole. So, I have this video clip which is about 5 minutes, I think.
Imagine traveling to a distant galaxy in an instant. What if we could bypass the vast cosmic distances, taking a shortcut to reach the farthest corners of the universe? This is the tantalizing possibility offered by wormholes, theoretical tunnels that could connect distant points in space-time. While still firmly in the realm of science fiction, the concept of wormholes arises from the very real equations of Einstein's theory of general relativity. The universe is vast, filled with billions of galaxies, each containing billions of stars. The distances are so immense that even light, traveling at the fastest speed possible, takes billions of years to cross the cosmos. The idea of traversing these distances in a human lifetime seems impossible. Yet, wormholes offer a glimmer of hope, a potential pathway to explore the universe in ways we never thought possible. Could these cosmic shortcuts be the key to unlocking the universe's greatest secrets? The concept of wormholes emerged from Albert Einstein's groundbreaking theory of general relativity. In 1935, Einstein and his colleague Nathan Rosen published a paper describing these theoretical objects, which are more formally known as Einstein-Rosen bridges. Their work showed that the equations of general relativity allowed for the existence of these space-time tunnels. Einstein's theory describes gravity not as a force, but as a curvature of space-time caused by mass and energy. Imagine a bowling ball placed on a trampoline, causing the fabric to sag. This is analogous to how massive objects warp space-time. Now, imagine a tunnel forming, connecting 2 points on the trampoline. This is a simplified way to visualize a wormhole, a shortcut through the fabric of space-time itself. A wormhole is envisioned as having 2 mouths, each resembling a sphere or a black hole, connected by a narrow tunnel called the throat. Entering one mouth of the wormhole, a traveler could emerge almost instantaneously at the other mouth, potentially light years away. This journey through the throat, however, is not without its challenges. The intense gravitational forces at play within a wormhole would be immense. These forces could stretch and compress anything entering the wormhole, a phenomenon known as spaghettification. Furthermore, the stability of the wormhole itself is a major concern. According to general relativity, wormholes would likely collapse instantly unless supported by a strange and exotic form of matter. Section 4. Exotic matter, holding open the doorway. The immense gravitational forces within a wormhole would naturally cause it to collapse upon itself, closing off the shortcut. To keep a wormhole open and traversable, physicists believe a strange ingredient is required: exotic matter. Exotic matter, unlike anything we observe in the everyday universe, possesses negative mass and negative energy density. While negative mass might sound like something out of science fiction, it is theoretically possible within the framework of certain physics theories. If exotic matter could be harnessed, it could potentially counteract the inward pull of gravity, providing the outward pressure needed to stabilize a wormhole and prevent its collapse. However, the existence of exotic matter remains purely hypothetical. Section 5. Time travel and paradoxes, the perils of the cosmic shortcut. Perhaps the most mind-boggling implication of wormholes is their potential for time travel. If we could manipulate the entrances and exits of these space-time tunnels, it might be possible to travel not just through space, but also backward or forward in time. This possibility, however, opens up a Pandora's box of paradoxes. One famous example is the grandfather paradox. Imagine traveling back in time and accidentally causing the death of your grandfather before your parent was born. This would create a paradox, as you could not exist without your grandfather. These paradoxes highlight the potential logical inconsistencies and challenges that time travel through wormholes could present. Section 6. The search for wormholes. Fact, fiction, and the future. Despite their intriguing possibilities, wormholes remain firmly in the realm of theoretical physics. Currently, we have no observational evidence to suggest that wormholes actually exist. Scientists continue to explore their mathematical possibilities and search for any signs of these elusive objects in astronomical data. While wormholes remain highly speculative, the pursuit of understanding them pushes the boundaries of our knowledge about the universe. The quest to unravel the mysteries of these cosmic shortcuts could lead to groundbreaking discoveries in physics and our understanding of spacetime itself. Perhaps one day, the science fiction dream of traveling through wormholes will become a reality, opening up a universe of possibilities beyond our wildest imagination.
Okay, welcome back. Well, we have finished today's lecture. If you have any question, you are most welcome.
Yeah, assalamu alaikum.
Wa alaikum assalam.
Yes, this is Malik Salah, your PhD student.
Malik.
Yes.
Yes.
Thank you very much, sir. It was a wonderful lecture, and we were indeed, updated.
Okay, thank you.
Well, my question is, do wormholes exist in reality? Do they really exist, wormholes?
No, they don't exist, as you have just learned. They are theoretical concepts. But people are working
okay.
to
They are just
have some clue.
Okay. Thank you very much, sir. Thank you.
Any other question from the audience? So if there's no question, then we close our lecture, today's lecture here. And tomorrow is the final day, and we shall try to cover cosmological applications of GR, and then some techniques to find the solutions of Einstein field equations. And as usual, your question, answer, and feedback. Thank you very much. So, bye.